All right, in grade three students, we are on the second to last topic of this unit. I'm going to go ahead and tell you that we have a test coming up on February the 5th, which is Friday. So two more topics, and today's is going to be called coordinate quadrilateral proof. So let's go ahead and get started. All right, so the first thing you see on here is a diagram where we're talking about quadrilaterals. So at the top, let's do this. Draw a line in your notes to separate this, and then title this section Coordinate Quadrilateral Proofs. And then what I'd like you to do is draw this diagram. This is our hierarchy of quadrilaterals, okay? So I'm going to pause the video and have you guys write that. All right, so you've had a moment to write that down. So let's talk about the idea behind this. And you've written down this this chart here. Now, every single shape is a quadrilateral, and as this goes down with the arrows that are connected here, every shape is taking on properties of the shape before it. So a quadrilateral, the definition that we have, is a four-sided figure or four-sided polygon, and every shape branching from this meets that requirement, right? But a quadrilateral in reality, and I'm going to draw one really quick, is kind of boring. Okay, so for instance, this is a quadrilateral. It is a four-sided figure. So these special names of these shapes, where did those come along if we're thinking in a history standpoint? So mathematicians or people playing with these shapes, obviously they didn't have this tool here where they can just move it around, but they would just sit all day making these four-sided, these quadrilaterals, until they saw some really interesting patterns happen, like this one right here. Which this isn't a perfectly constructed one, but they noticed, opposite sides parallel, and they named it. They said, okay, this is a special type of quadrilateral. It has special properties. It's a parallelogram, okay? And then they said, okay, well, let's see what happens. Let's see if we can keep the same. Let's keep sides parallel, and then we get here. Said, well, there's perpendicular angles, 90-degree angles. Let's call this one a rectangle. Okay, we got that. Slide this over. All sides are the same. Call that a square. So that's what really happened when we're originating the names of these shapes, right? They were moving them around, and a quadrilateral by itself is not anything special, right? It's just four-sided figure. But we have these special cases that were discovered within it that we want to make sure we talk about, okay? And we're going to be doing what's called proofs. And this is a loose interpretation of a proof. There's other ways in geometry that we could do proofs, but we're going to be doing them with coordinates, okay? But first we have to talk about what makes a parallelogram a parallelogram. Well, you should be referring to your definitions as we're thinking through this. But I want you to, I know you just drew your hierarchy, but I want you to fashion your notes like this. We're going to be putting bullet points underneath each one of these. So I would say parallelogram, then go down 3 spaces, write rhombus and rectangle sort of on the same tier, a couple spaces down, then put in the middle square. And then we're going to draw some arrows to these. I'll get everything set up 1 second. All right, so I've got my diagram set up, and you're going to want to have something similar to this. And then we're going to be putting some bullet points down below these. So what makes a parallelogram a parallelogram? Well, the main rule for parallelograms is that opposite sides are parallel. That's important. All right, that is the rule for parallelograms. Now, there's also one other sort of consequence of this, and if you show either one of these, you're kind of proving that it's true. Obviously, the opposite sides parallel is the main one, but opposite sides are also congruent. And remember, congruent means equal in measure. All right, so they're lengths. And that's it. That's all it takes. If we can show that opposite sides are parallel or opposite sides are congruent, then ta-da, we have shown that it's a parallelogram. Okay? Now what these arrows are doing is saying, okay, all of these properties are inherited by the rectangle and the rhombus. So a rectangle has to have opposite sides parallel. That makes sense, right? If I draw one, I know that, here we go, we'll draw a rectangle. Here it is, right? Rectangle. There it is. A rectangle. Opposite sides are still parallel. We know that. Opposite sides are congruent. And from the first time that you ever saw a rectangle, you knew these rules because I'm sure your teacher taught you those. But what is it that makes a rectangle? What did the mathematicians see within a rectangle and say, okay, we can't call it a parallelogram. It has a special case. Well, that's that the angles are, and we're going to say this, angles are 90 degrees. There we go. Angles are 90 degrees. All right. And that's all it takes. So all three of these properties mean you have a rectangle if you've shown those. All right. What about a rhombus? Well, let me construct a rhombus really quick and put an image in here. So I put a rhombus here right above it. And what we notice about the rhombus is you have opposite sides are parallel, opposite sides are congruent, but it is lacking the idea that the angles have to be 90 degrees. So that's what would make it a rectangle, okay? So for a rhombus, the main rule here is that all sides are congruent. That is the rule. Now that also sounds a lot like a square, right? A square has all sides congruent. But the special property about a square is their angles, all four angles are going to be also 90 degrees. Okay? So the square inherits all of the properties listed. So every single property up here has to be true and has to be shown for it to be a square. Okay? So we're not going to even put anything under square. I guess we'll just put parentheses, all properties prior are shown. Okay? That's how we show that it's a square. All right? Now we're going to come back and do a trapezoid and a kite later. But let's go ahead and look at some examples of what we're going to be doing with this. So I'm going to pull Delta Math over. And what I'd like you to do, this is the first problem, so let me go back here. This is Coordinate Quadrilateral Proofs 1. You have 8 problems that you'll be doing here. And you get 10 attempts on these because here's the problem with this question. This is one that I made. There's 15 parts to it. All right, there's 15 parts. And one of the things about Delta Math that's kind of frustrating with this is that it won't tell you what you've missed. It'll just say the whole problem's wrong. And it won't say, hey, you missed the slope or you missed a length or one of these little pop-down menus here. You didn't, it won't say that, okay? All right. So, that's going to probably be a little bit frustrating. I might even increase the attempts, but if you get stuck on something, say a few attempts, and you just can't figure it out, this is a pretty long page as well. So, you find a way to ask for help. I can check the work for you and let you know where the mistake is if you're desperate for it and you're having trouble finding it. But hopefully finding the mistake is, that's part of it. But you only have 8 problems to do this. So let's talk about the proof aspect of this, okay? It says, prove the shape you see by using the appropriate calculations and justifications. So obviously, the first time that this is introduced to students, they're like, well, Mr. Woods, it's a rectangle. I can see it, right? That's how students think. That's what they do. Yeah, I can tell that it is a rectangle. But that's not good enough for what we're trying to do, okay? You have to actually prove that it's a rectangle. So how are we going to prove that this is a rectangle? Well, we have to show that the angles are 90 degrees, We have to show that opposite sides are congruent, opposite sides are parallel. So all three of those properties have to be true in order for it to be a rectangle. So let's do this in our notes. So in your notes, let's put example, because we're going to be doing this one together. And it's going to be this first one here. And what I'd like you to do is I would like you to make yourself a quadrilateral that looks, it's going to be like this one, so it's going to look like a rectangle. I don't know if I can pre-draw the shape that I want here. I'm going to try to, but you can go ahead and in your notes start drawing this. Yeah, right. Okay, that's not going to work. I'm just going to have to freehand it. No, okay, hold on. Draw mine. So you're going to draw something like this, and it doesn't have to be perfect at all, so don't worry about that. All right. And then we're going to label the points. We're going to say A. And then we also want to put the coordinates with it because this is coordinate geometry. So what's the coordinate of A? Well, it's -5, comma, -1. Looking at our scale. So let's go ahead and list all of these. Okay, so A right there. B is going to be, let's put the coordinate. It's -4, 3. Alrighty, let's do C. So C is going to be, that is positive, let's see, 5, 6, 7, that's +8. Y value 0. So we'll put that, come on, move that over here. We'll put the C right here. And then lastly, D is going to be, D is going to be 7, comma, 7, comma, that is -4. All right, so we have our rectangle in here. So what we need to be able to do is we have to prove that, these properties here, okay? Angles are 90 degrees. And I'm going to copy these in. You have these up above, but I'm just going to make sure that I have these in here. So we're trying to show all of these are true. I'm going to sort of check mark them as we get it. Okay, so first off, opposite sides are parallel. Well, we've talked about how parallel lines work on a coordinate plane. What has to be true for lines to be parallel? Well, and you can already kind of see right here, we're looking, it says find the slope. Well, it has to do with slopes. And remember, lines that are parallel will have equal slopes. So let's actually go back here and let's add an extra bullet point underneath here, like a sub point, or you can draw an arrow or something. It says opposite sides are parallel. So we need to show slopes of opposite lines are equal. That's what we want to do first. That's what we want to do first. So we have to actually calculate this to show it. So what I'm going to do this is I'm going to be looking at the rise over the run. Let me change to a dashed line. Okay, so here is the rise of this point and then the run. I'm going to repeat this for all of them. This one is going to be red just so that we can compare them, because we're trying to show that the ones down here are the same. The bottoms are the same. Okay. And the ones on the side are the same. So really all we need to do is list the rise and the run. So over here, how much did we rise? Well, you can actually count on the picture. It goes 1, 2, 3, 4. Okay, so it's 4. I'm going to put that on there. And then the run, let me move this, and you can also use the coordinates to do this as well. The run is, we move over 1. That's it. Okay, rise 4, run 1. So inside of here, and what I'd like you actually to do is right, you can do something like this. So you write slope, and then go ahead and put AB, and that's equal to rise over run, so it's 4 over 1. So there's our slope for that first one. Then we're going to go to the next one. What's the run? Well, it goes from -4 to +8, so the run is +12. What's the rise? Well, it goes from 3 to 0, so it actually goes -3, and we have to remember to consider our signs for this. So there's our rise and our run. So for the slope of BC, it's equal to rise over run, so it's -3 over 12. Okay. Then we want CD. So CD is going to be -4. So it goes down 4 from 0 to -4. Move over so I can 0 to -4, and then move that over, and then it's going to go over -1. So for CD, get -4 is the rise over -1. Okay, good. Last one we need is this from D to A. Okay, so let's do that one. So it goes -12 back. You go from 7 to -5, you're taking away 12 on the x value. And then -4 to -1 is positive +3, yeah. So the rise is 3 over -12. So then we simplify all of these. So the slope is 4. Right here, it's -1 over 4. Then we get 4 again, and then we get -1 over 4. So what we're looking for is to show that opposite sides, so AB and CD, are they equal slopes? Yes, 4 and 4. All right, so in delta math, how I would start this, so let's pull this up. I would type in a 4 here. I'd go down, I'd do -1 divided by 4. Type a 4 here, and then -1 divided by 4. And that's going to be what you start with, okay? And this is showing you that opposite sides are parallel for both. All right, so back over here, we have successfully shown this one, okay? Now we can also show something else with just the slopes. We can also show that the rectangle, or that it's a rectangle with the angles. How do we show that angles intersect at 90 degrees with slopes? That's something else that we practice. So parallel is equal, but 90 degrees, remember, we call that perpendicular, right? So let's go back here. Perpendicular, right? That's what that property is called. How do we show that? Well, slopes of adjacent sides are, how do we show perpendicular? Remember, that's the opposite reciprocal. Opposite reciprocal. Okay. Slopes of the adjacent sides are opposite reciprocals. So is that what's happening here? Here is AB. The slope is -1/4. That's the opposite, so it's negative, and you flip it, it becomes 1 over 4. So these two sides we've shown are 90 degrees. Then you'll notice you flip and change the sign from BC to CD, so this side and this side are 90 degrees. Then CD to DA, okay? CD to DA is 90 degrees, and then DA to AB, so back here, it's also 90 degrees. So we've actually shown, because it's flip, change sign, flip, change sign, flip, change sign, and it just keeps that pattern, that every single angle is 90 degrees. So that's what we do with this, okay? That's what we have here. All right, cool. Now, the next thing that we have to show the next thing we need to show is that all the sides are opposite sides, excuse me, are congruent. That has to be true. So how do we show opposite sides are congruent? Well, we need to find how long they are. So that is the next section here. We have to find the length of all these sides. So you're going to repeat the exact same thing that we did. I'm going to copy this. Okay, and let's go back. So we're going to do the same thing we just did, except now we're going to say length. Instead of slope, we want length. I'm going to paste this in. Move this down here. So you're going to copy that down. All right, length of AB, BC, CD. All right, so we need an idea. How do we find the length of this? Maybe you're already thinking about it, because when I introduced this in to face-to-face students, several people came up with the idea. Well, these are right triangles, all of them, right? And so right triangles, we can use something called the Pythagorean theorem, which is the formula that literally every single student remembers forever. Oops, sorry about my screen. I'm trying to move my camera over. There we go. It's the formula that every student ever remembers. So for AB, so let's set this up. So it's Pythagorean theorem, a squared plus b squared equals c squared. All right, so what does that look like here? Well, we'll just call this A, it doesn't matter, this is B. And so we get 4 squared plus 1 squared equals, well, we don't have C squared, but we have AB squared, right? We're just gonna call it AB, because that's what we're trying to find, the length of it. So we're gonna write this up, it's gonna be 16 plus 1 equals AB squared. And then all we have to do is square root both sides. It's going to be 17, so it's square root 17 equals AB. We've got it, okay? And you'll notice that the formula for all these sides is going to end up being square root of A squared plus B squared. Okay, that's what's always going to happen. You're going to square each leg of that. Well, really, it's the slopes. If you notice that it's the slope, you're squaring each part of it, not the simplified form like we simplified it here, but it's the unsimplified slopes. Those represent the legs of the triangles, and we square them. So let's do this one. It's going to be square root of 12 squared plus. Hold on. 12 squared plus, we want -3 squared. And now, normally you can't have a negative length, but because we're squaring it, it gets rid of it. This ends up being square root of 144 plus 9 equals, so that's going to be square root 153. Okay, that's how you do that. Now, we actually end up getting a new formula that appears from this. So we're going to write this down in our notes. We're going to call this the distance formula. I think some students said that they had actually seen this one before, so not entirely sure if everybody knows this one, but this is what we're going to be using. Distance is equal to, we have, let me find my square root button here. I've actually never used this math type function. I actually just saw it, so I'm gonna actually skip ahead to where I've gotten this written. All right, I don't know why. I could have probably just copied this in from a website, but instead of sweating over trying to get it copied in, and now it's messing up on me still. Oh no. Why? There it is, okay. So there's our distance formula. So go ahead and write that in your notes. And essentially you'll notice it is the exact same thing as this. It's just the change in x squared plus the change in y squared that equals the distance between the 2 points, okay? So we don't really have to think about that too much in this example, especially since we see the changes. But you'll notice that several of them are negative, and we have some positives. But we can go ahead and do this. So for CD, I'm going to do negative 4 squared plus negative 1 squared. Also, order doesn't matter as far as, like down here it says x2 minus x1 squared plus y2 minus y1 squared. If you looked this up online, it would probably have them flipped. But because addition is commutative, it really doesn't matter what the order is. And that's always been true for right triangles, okay? So we get, this is going to be square root 16 plus 1, which is square root 17. Okay? And then finally, we do the last one, which is negative 12 squared plus 3 squared. There. And so we get 144 plus 9, which is going to equal which is going to equal square root 153. And so now you're noticing that we have AB and CD, they are congruent. BC and DA are congruent. And that's exactly what we wanted to show. We wanted to show that opposite sides are congruent. And now we want to also add this note in here. How do we do that? Here, show opposite sides have equal length. This formula. Okay. And if it's just straight up and down vertical or horizontal lines, usually you don't even have to use the distance formula. You can just count, right? If they're exactly horizontal. But I would say in most cases, the distance formula will always work because some examples you don't even see the shape, which we're going to do one of those. I know we're already 30 minutes in. So I might actually just stop this lesson early and then pick up with another example on the next one, just to keep this one a little bit brief. But let's go ahead and work through the delta math here. Let's look at what we need to do. So the length of AB that we got was the square root of 17. That's what we got. So let's talk about how to type that in. You have a little button at the bottom here. Let me move my camera back over now. Camera over. You have this little button, square root, that if you click inside of here and go down, it'll add the square root. So that's 17. You could also type, if you're using a keyboard. Now, if you're on a phone, you're going to want to use the button. But if you are on a keyboard, you can type SQRT and you can type in the number, which is fine. Now we know, so I kind of like doing that actually. So these are going to be congruent. Okay. And that's really, once you do that, you pretty much have all the information you need. If you find all the slopes and all the lengths, you can prove it's any of these shapes. All right. The main thing for rhombuses is all sides are congruent, and a square, all sides congruent. Obviously, not all sides are congruent. So this is definitely not a rhombus or not a rhombus or a square, but we're seeing that opposite sides are parallel. And then the biggest thing about a rectangle is that the adjacent angles are perpendicular. So now we fill in these bubbles. Opposite sides, are they parallel or not? Well, they are parallel. We proved that right here and here, here and here. Those are opposite sides parallel. Adjacent sides, perpendicular? Yes. That is the property we're looking for to show it's a rectangle. All sides congruent? No, that's not the case. If they were, then it would be a square at this point. Opposite sides congruent? Yes, they are. Adjacent sides congruent? No, they're not. And then we have the special rule here, exactly one pair of opposite sides parallel. No, that's not the case. We have two sets of opposite sides parallel. Based on this information, the shape is a rectangle. Now, parallelogram technically is correct, but you will get this problem wrong if you put that. We need to be more specific. So we hit submit. Again, these are all the parts here. We hit yes, and we got it right. Now, If you get it wrong, it's not going to tell you what you missed. Okay, so you're going to have to go back and recheck calculations, make sure that all of your statements are true. So that's going to be the big thing. Now, I do want to write down these last two. So write down in your notes below the example properties for a trapezoid. And this is all you have to show for a trapezoid. If you have a trapezoid, pretty much all of the drop-down boxes are going to be no's. Like a trapezoid, let's draw a picture of one. I think they actually have a shape in here that we can use. Here's one now. This is an isosceles trapezoid actually. But you have exactly one pair of parallel sides, okay? These sides here are going to be not parallel. That also means that you're not going to have any 90-degree angles. Opposite sides, in this case, these opposite sides are congruent, but not all the sides here are congruent. The top and the bottom here are not going to be congruent. So the rule for a trapezoid is exactly one pair of opposite parallel sides. Okay? So you just have to show that the slopes are equal on the top and the bottom. All right? Now let's talk about a kite. Okay, so here is an example of a kite. And what you'll notice is that the side AB and AC are going to be congruent, and then the sides BD and CD are congruent. All right? So to show that a shape is a kite, you have to show that two pairs of congruent adjacent sides. All right, so that's all you need to do. So you have to use the distance formula to do this. I would show this is congruent to this, this is congruent to this. Now you'll notice that these opposite sides are not parallel. AB is not parallel to D. So that would be the case there with that one. All right. So I'll probably do one more example for the next lesson, as well as, because let's look at this fourth one here. See the problem? Here we're given shapes. So it's a quadrilateral mic has these vertices, and you're using coordinate geometry to prove what shape is created by these ordered pairs. And it's the same fill out here for all of this, but now we don't have a visual, okay? So you're having to do all of the same steps with no visual. So you have to remember all of these properties that we wrote down to prove the shapes, okay? And remember that kite and trapezoids are not parallelograms. So as soon as you see that the sides aren't, as soon as you show that the opposite sides aren't parallel, then you should be thinking it's a trapezoid or a kite, okay? Now there's also an option that's possible that it is none of these. We didn't see that on the first example, but you may get a shape in here that it's none of them, all right? Where it's just a quadrilateral, the top part, where it has four sides, and that's it. There's nothing else special about it. All right, so I'll stop the video here. Let me know if you need any extra help. I will be doing one more example in the next lesson. That'll probably come out tomorrow or the next day.